Welcome to Cosmos Game. In our today's class, we will be learning about dipole. So what is a dipole? I take two equal and opposite charges, which are separated by a very small distance, or a finite distance, then this whole thing is called as a dipole. Remember that the charges are going to be equal and opposite. That means if this is plus 5, then this should be minus 5 coulomb. So this whole concept, a pair of two equal and opposite charges separated by a very small or finite distance, this is called as our dipole. So I take a charge here and I take another charge here which is equal in magnitude, separated by a distance, finite distance, or very small distance. This setup is called as a dipole. For example, let's take minus 3 coulombs here and here plus 3 coulomb separated by a distance. Then this setup is called as a dipole. So I'll define my dipole as a pair of two equal and opposite charges separated by a small or finite distance is called as a dipole. Now, let's try to learn the concept of dipoles, how we denote it or how we represent it. Concept of dipole. So, a dipole is always consists of two equal and opposite charges separated by a small or finite distance. We always denote the distance between the two charges to be 2a. Remember that the distance between the two equal and opposite charges is denoted by 2a. If I take the center of the dipole as O, since the total length is 2a, and this is the center or midpoint, each distance from the center to the charge will be given by a. So the total length distance between the two charges becomes 2a. So here the distance between the charges is taken as 2a. As 2a. Another concept here, the next concept is going to be, I take a dipole here I draw a line passing through 2 points, a straight line. Then this line is called as our axial line or horizontal line. when I draw a straight line passing through both the charges horizontally, this line is called as axial or horizontal line. In the same concept, I take a dipole from the center. I draw a straight vertical line along y-axis. This line is called as perpendicular line or vertical line. So, in the next topic, we'll try to find electric field due to this dipole at any point along the axial line and electric field at any point on the perpendicular or vertical line. Now, let's try to learn dipole moment. Dipole moment. I take a negative charge here, take a positive charge here of equal magnitude separated by a distance here. The distance between them is 2a. So my dipole moment will be given by P equals magnitude of either of the charges. That means not considering their sign multiplied with the distance between them. So this gives me my dipole moment. Our dipole moment is a vector quantity and it will be always directed from negative to positive charge along the direction of negative to positive charge. So I'll define my dipole moment as the magnitude of either of the charge multiplied with the distance between the two charges. So it is defined as the product of magnitude of either of the charge to the distance between the two charges in dipole. Now, as I said, dipole moment is a vector quantity and is always directed from negative to positive charge in a dipole. That means it is opposite the direction of electric fields. So it is a vector quantity which is directed from negative to positive charge. I can say it is opposite the direction of electric fields. Mathematically, the magnitude of electric dipole moment is given by P equals 2AQ. So this formula will give us the dipole moment using the dipole moment formula. Try to solve this question. Now in here, note, we know that dipole moment is given by P equals 2AQ. Product of magnitude of either of the charges to the distance between the two charges. So from here, I find that Q is measured in coulomb and distance is measured in meter. So my SI unit of dipole moment is coulomb meter. The SI unit of dipole moment is coulomb meter. Now we will try to learn what is electric field at a point on the axial line of the electric dipole. Remember the axial line, we are going to use that concept. Now consider two charges minus Q and plus Q forming a dipole here with center O. Let's say this point is at A, this point is at B. If I draw an axial line that goes along this is my axial line. I consider any point here. Let's say this point is B. Plus Q charge is going to be given an electric field on this in the direction. At point P, there is going to be a test charge, which is always positive. So it will be a repulsive force. That means it is going in this direction. So the electric field at P, given by plus Q, is denoted by electric field plus Q. Because of minus Q, an electric field will be acting on point Q. So that electric field will be an attractive force that is in this direction. So let's say it is given by E minus Q. Whenever we consider any point here, it is measured with respect to the center of the dipole. So let the distance from O to P is denoted by R. Now we want to find the total electric field at point P due to this and due to this. We know that the distance from here to here is going to be A from the concept of dipole A. And the dipole direction is always from negative to positive. So P direction is from negative to positive charge. Consider a dipole consists of charges minus Q and plus Q separated by a distance 2A. Let P be any point on the axial line of the dipole. Our distance from the center. Now, from the diagram, we find that OP is going to be R, and the distance of P from charge plus Q will be R minus A. R minus A, that means BP is going to be R minus A, whereas the distance from minus Q to P is going to be R plus A. So, from diagram, we find that OP is going to be R, BP is going to be equal to R minus A, and AP is going to be equal to R plus A. Now, we'll try to find the electric field at point P due to plus Q. So, electric field at P due to plus Q in magnitude is given by E plus Q is going to be equal to 1 by, using the electric field at any point formula, I get 1 by 4 pi epsilon naught Q divided by, the distance from here to here is BP, so BP is R minus A whole square. Similarly, the electric field due to minus Q at P is given by, similarly, the magnitude of electric field at P due to minus Q is given by E minus Q is going to be 1 by 4 pi epsilon naught Q divided by, now the distance of minus Q with P is AP, and AP we know that it's given by R plus A. So R plus A whole square. Now from here, we can find that plus Q is closer to point P, whereas minus Q is further from point P. That means the electric field given by plus Q, this will be greater than the electric field given by minus Q. And they are opposite in direction. So the net or total charge, total electric field due to the charges at P will be given by the electric field with greater magnitude minus electric field with lesser magnitude. The minus comes because they are opposite in direction. We can explain it in vector form as well, but this will be the easier way to draft it. But we find that E plus Q is greater than E minus Q and are opposite in direction. Therefore, the total or net electric field acting at P due to the dipole is given by E is going to be equal to E plus Q minus E minus Q. E is going to be, when I substitute this value, I get 1 by 4 pi epsilon naught Q divided by R minus A whole square minus 1 by 4 pi epsilon naught Q by R plus A whole square. I take whatever common is here from here, Q by 4 pi epsilon naught. What is left is 1 divided by R minus A whole square minus 1 divided by R plus A whole square. I try to solve the terms inside the bracket. Q divided by 4 pi epsilon naught. Take the LCM, R minus A whole square, R plus A whole square, R plus A whole square minus R minus A whole square. So this terms becomes Q by 4 pi epsilon naught R square plus A square plus 2AR minus R square plus A square minus 2AR divided by R minus A R plus A whole square. This term can be compressed using the formula A square minus B square equals A minus B, A plus B. I can compress back here. So Q divided by 4 pi epsilon naught, the upper term, I'll open the inside bracket, R square plus A square plus 2AR minus R square minus A square minus plus 2AR divided by R square minus A square whole square. This term will get cancelled because they are equal and opposite in sign. So what is left is Q by 4 pi epsilon naught. I plus these two, I get 4AR divided by R square minus A square whole square. Now we know that these two are separated by a finite or very small distance. So if I take a half, that means it's going to be even getting smaller. Therefore, comparing this A with R, A is going to be very less. So we are going to neglect this comparing to our R. But R is much more greater than A. So we can say that A square is equivalent to 0, or we can say that A square is neglected. Thus, the above term E becomes Q by 4 pi epsilon naught 4AR divided by R square whole square, because we have neglected, or A square is equivalent to 0 because it is very small, and when we square it, it will be very near to 0. E equals Q divided by 4 pi epsilon naught. This 4, I can split it as 2 A R divided by R to the power 4. 1 R will get cancelled. So 3 R's are left in the denominator. E equals Combining all these, I can write P. So 1 by 4 pi epsilon naught P. In place of all these, I can write P, which is dipole moment divided by R cubed. Now in magnitude, this will give us our electric field acting at point P due to our dipole consists of minus Q and plus Q. In vector form, E is going to be equal to 1 by 4 pi epsilon naught to P vector, because P is a vector, divided by RQ. So this gives us the expression for electric field or formula for electric field at any point on the axial line due to a dipole. Now, try to find the answers of these questions using the above formulas and derivations. The second question, which I have not given, try it yourself. If you want me to show you, let me know in the comment section. With this, we are going to end today's class.